Hello everyone. Today we're on tutorial 1, first year university physics, vectors, going on to part 2. Okay, let's go to my notes. Now this is the part where is the basis of our mathematical calculations, representation of vectors in terms of components. Any vector can be considered as the sum of two or more vectors. Each vector of the sum is called the component of the resultant vector. Thus, in the earlier example, A and B are called the components of R. If you remember, we added A and B to get a resultant. A and B can be thought of as the components of the resultant R. When a vector is expressed in terms of components, the vector is resolved into components. I'll come back to this in the resolving in a minute. I think I'll do it on the whiteboard, but before that, let's go a little bit further with the notes and I'll come back to it. For calculation purposes, it is convenient to express vectors in terms of two orthogonal means perpendicular, in terms of two orthogonal components. This bracket should be here. Usually horizontally and vertically, but in problems involving slopes, it is more convenient to express the vector in terms of components parallel and perpendicular to the slope. We will encounter many examples involving the two cases in the tutorials that follow. Okay, let's look at resolving vectors. Let me take a vector R and let me add a number of vectors. Together to get so we say that A, B, C, D, E, which add up to make R. Notice the R takes us from the same start position to the same finish position. We call A, B, C, D, E the components of R. And then we say the vector R is resolved into components. And we can write this vectorially like this. But actually, when we talk about resolving a vector into its components, we normally mean resolving it into horizontal and vertical components. Let me call this vector A. The horizontal component, the vertical component, and let me call the horizontal component AX and AY. Now this is my vector A. Now the components have to go from the start position to the finish position. Again, imagine yourself walking. If I walk from here to here, then my two vectors must take me to the same endpoint. So I have to walk in this direction and this direction. So this tells you the direction of the components. In many physics problems, it's convenient to resolve a vector into its horizontal and vertical components. Now we can also do this, and it's sometimes more convenient. Instead of using a triangle, we can use a rectangle. With a vector as the diagonal of the rectangle. The components now are the two sides of the rectangle. The horizontal component and the vertical component. Now what about the directions? Again, if If you look here, we have to go from the same starting point to the same finishing point. Now the direction of the components with the rectangle have to be exactly the same. And the way to remember the correct directions for the rectangle is that all three vectors point away from the start point. If this is the start point of the vector A, then A points in this direction. Then the AX must also point away from the start point and away from the start point. Another way to look at it is all their tails are tied together and all three vectors point away from their tails. Of course, as any vector should. So many problems then, it's convenient to resolve in vertical and horizontal components. And in fact, mathematically, subtracting and adding vectors is much easier in component form than perhaps using sine rules, cosine rules, etc. But another convenient way of resolving, again with orthogonal vectors, but this time parallel and perpendicular to slope. So let's look at resolving vectors parallel and perpendicular to slope. This is a right angle triangle. This is theta. This is mg. So what I do to resolve this is to draw a rectangle with mg as the diagonal, and I draw the rectangle with one side perpendicular to the slope and the other side parallel to the slope. So my components of the vector are the two sides of this rectangle. Now to get these two, I need to find this angle. Now, what is this angle? Let me redraw this and just focus on now I'm drawing this at point A. So this is here is point A. Let me divide this triangle up. This is theta. This is where my mg is going to be. Now you can see if this is a right angle, this is 90 minus theta. This is also a right angle. Remember, we're resolving perpendicular to the slope. This is a right angle. So if this angle is 90 minus theta, this angle is theta. So using this geometrical construction or construct, we can deduce that this angle here is theta. Now I have a right angle triangle now. This is the adjacent. And by the way, when you're doing sines, cosines, and tangents, instead of going through the rigmarole of writing SOHCAHTOA and rearranging to find the adjacent, you can always remember the adjacent is always going to be the hypotenuse multiplied by cos. The hypotenuse here is mg, so this becomes mg cos theta. This side here is the same as this side, which is the opposite. So down the slope is mg sine theta. So when you are doing these kind of calculations using trigonometry, instead of writing the definition of cos and rearranging, just remember the adjacent is always the hypotenuse multiplied by cos theta. This gives me the adjacent. The opposite is always the hypotenuse multiplied by the sine theta. So try to remember that. It saves you a bit of time in calculation. Alright, so this is resolving a vector into its orthogonal components, either horizontally or vertically, or parallel and perpendicular. Let's go back to the notes. We come now to defining unit vectors, which is a very powerful way of treating vectors. A powerful way to express vectors used in any advanced treatment of vectors is to express them in terms of unit vectors ij in 2 dimensions and ijk in 3 dimensions. So in 2 dimensions we have I pointing in the direction of the x-axis. Its magnitude is 1. And we have the vector j pointing in the direction of the y-axis, and its source magnitude is also 1, which is what we mean by unit vectors. In terms of these unit vectors, any other vector can be expressed. If we take a vector A, then the projection of A onto the x-axis is AX. You can see that if you multiply I by AX, we're going to end up with a vector which is the x component of the vector A. Similarly here, if AY is the projection of A onto the y-axis, then if I multiply this by j, I end up with the y component of the A vector. I can therefore write A as the sum of these two vectors, AXI plus AYJ. AXI is the x component vector of A, AYJ is the y component vector. The coefficients AX and AY are what are called components of the vector. So AXI and AYJ are the orthogonal component vectors of A, while the coefficients AX and AY are called components of A. Similarly, in 3 dimensions, we have, again, I in the x direction, j in the y direction. Now we have another unit vector, k, in the z direction. And although it's difficult to draw, again, the box helps us. If we draw a box with the A vector as diagonal, and the sides of the box give me the coefficients AX, AY, AJ, and the sides of the box are the actual component vectors of A. So I can express A in terms of AXI, AYJ, AZK. AXI, AYJ, and AZK are the component vectors. AX, AY, and AZ are what are called the components of A. Perhaps it will help you if I draw this on the whiteboard. Draw my y-axis. I is a unit vector in the x direction. J is a unit vector in the y direction. Now let's draw a vector A. The projection of A onto the x-axis, I drop the perpendicular down. Let me call this length AX, and then I project the vector onto the y-axis. This length is AY. Now if I multiply J by AY, I get the y component vector of A. And if I multiply AX by I get the x component vector of A. So you can see that I can add these vectors to get A. So I can do A equals AX I plus AYJ. So you can see that I can express any vector in this form. If I have a vector in this quadrant, then my x is going to be negative and my y is going to be negative. Whichever way, wherever I draw a vector, I can always express any vector on the xy plane in terms of I and j. Similarly in 3 dimensions. Though it's more difficult to draw, mathematically there is really no more difficulty in treating 3-dimensional vectors in terms of components as it is treating 2 components. Again, I draw a box. To kind of guide me in drawing the A vector. Again, I have I along the x-axis, unit vector j along the y-axis, and unit vector k along the z-axis. Now if I draw my vector as the diagonal of the box, not very well drawn, but it's a diagonal from this corner to the opposite corner. Then again, if I project onto the x-axis, that length is ax, ay. So you can see that ax, ay, and az are the sides of the box, of which the a vector is the diagonal. So again, using the unit vectors, I can write my vector in 3 dimensions. So there we have it, expressing vectors in terms of unit vectors. Before going back to the notes, let's look at the meaning of a vector equation. Let me add 2 vectors to give me the resultant R. Now this is a vector equation, and although I can rearrange this much like an algebraic equation, for example, I can make B the subject. A goes across the equal sign and becomes a minus. Or I can make A the subject. So though I can rearrange the vector equation similar to an algebraic equation, there is a difference that you need to understand. This vector equation, if you like, you can think of it as combining 2 equations. Let me first use the ij notation. So let's write this vector as axi plus ayj. My b is bxi plus byj. Then my vector r can be written as ax plus bx I plus ay plus by j. Now, although I've introduced you to ij notation, in your tutorials you're mostly going to deal with the tabular form, which I'll come to explain in a minute. So it may be convenient to think of the vector equation in the following way, which is basically identical to this, but it's just a way of writing that may make it a bit easier for you. And when using tabular form, this may also help you. So this equation, in fact, contains 2 equations. So if I split into components, this equation means Rx equals Ax plus Bx, Ry equals Ay plus By. So this thing you can think of as being equivalent to the vector equations. Anyway, perhaps it will help you to understand the vector equation if you think of it like this. Okay, let's go back to the notes. Adding and subtracting vectors in component form. We can represent 2 vectors A and B graphically 2 alternative ways with respect to a Cartesian coordinate system. The first way, I write my vector sum geometrically in the same way as before, except this time I do it with respect to the x and y axes. So I can draw my vector A starting at the origin. I take B and put it head to tail. Then my resultant is from the starting position to the finishing position and points in that direction away from the starting point. Now this is a good way to get a rough idea of the resultant. When you're adding or subtracting vectors, if you draw them graphically like this on the xy coordinate system, it gives us an indication of what R is going to look like before we calculate. But for calculation purposes, when we're adding, it's good to write the vector A and the vector B, both with their tails tied to the origin. Then we can calculate the component AX and AY, BX and BY using trigonometry. This is a right angled triangle, angle theta. This is a right angled triangle, angle psi. Now again, the angles that I want, mind you, always measured from the positive x-axis in the counterclockwise direction. So theta is already the angle that I want, but for B, I need the angle phi. But the best way to calculate, it's up to you. You can use the angle phi, but I prefer to use the right angled triangle, find psi, and then obtain phi as phi equals 180 minus psi. Okay, so when I draw my vectors in this way, it's easy for me to use right angled triangles to express the components in terms of the magnitude of A and the angle. So this is my expression in a unit vector form. My AX component is given by A cos theta. My AY component is A sin theta by ordinary trigonometry. And similarly, BX is B cos phi, B cos psi, I should say. BY equals B sin psi. And the angle phi that I want measured from the x-axis is 180 minus psi. I should mention some notation. Two parallel lines enclosing a vector mean that we take the magnitude of the vector. So this is a notation I'll be using a lot to represent the magnitude of a vector. Now, when we want to add, once you've got things in component form, addition is very easy. Because all we do is, let's think of AX, AY, and BX, BY. All I do is I add the X components and the Y components to get the resultant. So the resultant here is given by AX plus BXI, AY plus BYJ. Now to represent this on my coordinate system, I need to find, well, I can draw the vector immediately by drawing the components. Once I've added these up, I can then draw them on the Cartesian coordinate system directly and obtain the vector as a diagonal of a rectangle. I'll show you how to do that later. But we also want to calculate, in these kind of calculations of additions, we actually want the magnitude of the resultant, and we also want to know the angle the resultant makes with the x-axis. So again, the best way to show you this is in examples later. Or maybe I can just quickly show you on in general terms on the whiteboard. We'll be doing this again a bit later, but let me just do it quickly here. All right. So we've got two vectors. Let me try and do better than that. Okay, so I've got two vectors. I'm going to keep this in general. We'll come to plenty of examples later with specific numbers, which may be easier for you to follow. Now I want to add these two vectors to find my resultant. Remember, the AX, BX will be just numbers, AY, BY will be just numbers. So my Rx is equal to this, and my Ry is equal to this. And once I've found Rx and Ry, I can immediately plot these on the x-axis, whatever their values might be. Now, supposing Rx equals, let me give it a minus sign, 2, in arbitrary units. Ry equals 3. So I can immediately plot this. I can put minus 2 here, plus 3 here, draw a rectangle, and this gives me the resultant R. However, in a calculation, I want to know the magnitude of R, and I want to know the angle psi. Let me call this theta. This is different to what I've used in my notes on the previous page that we just showed you. But let me just use these angles now. So I can find the magnitude by Pythagoras theorem. This is a right angled triangle. This is the hypotenuse. And if I know the two sides of the triangle, I can use Pythagoras. So the magnitude of R is equal to Rx square root of Rx squared plus Ry squared. And again, by trigonometry, I can find theta. If I know the opposite and I know the adjacent, then tan theta equals, the opposite is Ry, the adjacent is Rx, so my theta is tan to the minus 1, or arctan if you like, Rx. Now I tend to take the positive magnitude. When I want to find just this angle, I just take the positive magnitude. Then I can find my psi from 180 minus theta. So these are formulas you're going to be using all the time. Okay? So this is adding vectors using components, and you can see how easy it is. I'll go back to the notes. Okay, here I've used alpha instead of theta. That's because I've used theta and psi before. I might mention this because some of you may prefer to use Ry and Rx in general form when they're plus or minus. So when we do this calculation, in fact, in either approach, the way you interpret this angle depends on the quadrant that the vector ends up with. So when you do this calculation and obtain a value for alpha, you need to know which quadrant it is for you to interpret the angle properly. So before you do this calculation, it is always good to draw the vector, as I did on the whiteboard, using the Rx and the Ry components. Because once you write these down, you know which quadrant it is. If both are positive, it'll be in quadrant 1. If Ry is positive and Rx is negative, then in quadrant 2. If Rx is negative and Ry is negative, quadrant 3. If Rx is positive, Ry is negative, then in quadrant 4. So once you've drawn this, then you'll know which angle alpha is and how to obtain your psi measured from the positive x-axis. Now to help you to do this, there are two approaches. So care must be taken in interpreting the angle you get from this formula. Now, what I'm going to do is to give you two approaches to find the right angle. So again, the first thing to do before you interpret this is to draw your Ry and your Rx. So if I get Ry in the first quadrant, I have this. This is my angle, so this is just straightforward. Phi is equal to theta. If I find the angle in the second quadrant, and the first approach takes the positive value of R and X. So I'm always going to get an angle that's positive. But I need to interpret what it is. So if it's in the second quadrant, theta is this right angled triangle. So my psi is given by 180 minus theta. If I end up with Rx negative, Ry negative, this gives me the R vector in the third quadrant. And the right angled triangle that I calculate, the angle I calculate from here is this right angled, the angle of this right angled triangle. So my psi now is 180 plus theta. Again, if my vector is in the fourth quadrant, this formula gives me positive theta, gives me this angle of this right angled triangle. So my phi is 360 minus theta. So if I always take these positive values, irrespective of whether Ry is actually negative or not, I get a positive theta. Approach 2 is I allow Ry to take their normal signs. In this quadrant plus plus, in this quadrant plus minus, in this quadrant minus, and so on. So this time the angle may be positive or negative. But again, care has to be taken in interpreting the angle. To help you understand this, I've chosen particular values of Rx. I've chosen magnitude to be 2 of Rx and the magnitude of Ry to be 4. So in my example here, my Ry and Rx are positive, so this is straightforward. Theta is equal to phi. And if I do my calculation with these Rx and Rys, I get 63.4 degrees. When I go to this side though, my Rx is negative, and the appropriate formula is 180 plus theta. So if I do my particular calculation, you see that theta comes out to be negative. So when I add theta, I'm adding a negative theta, so my angle phi is 117 degrees. You can even see geometrically what the angle ought to be. So these formulas are easy to remember just by looking at the geometry of the position of the R vector. When we come to this, the third quadrant, my theta is here. I've got minus minus, so this comes out to be plus. So I get a positive value, but again it's this angle of this triangle. So to get the right angle, I have to add 180 plus theta. The angle comes out positive, so I add it, and I get 243 degrees. In the fourth quadrant, this time the angle will be negative because I've got a minus and a plus, so it's minus 63.43. So it's 360 plus theta, but I'm adding a negative of the angle, so I get 297 degrees. So those are two ways you can do it. I tend to prefer dealing with positive values here, finding the angle of the appropriate right angle triangle, which you can tell by first plotting Ry and Rx, and then calculating phi accordingly to whichever quadrant it is, using any of these formulas. Okay, I hope this will help you in later calculations not to confuse the angles. Now using IJ and K notation is very useful, but in the course here, your lecturers tend to prefer using tables, and also you may also find this a lot easier than using IJ vectors. So in the calculations that we're going to do in the tutorials, I'm going to use this tabular method. It's exactly equivalent to using unit vectors to add the components. And let's look at this nice, easy way of doing it. You can choose the method you want if you want to use IJK vectors, or if you want to use the tabular approach. This method is based on the use of components, and although equivalent to adding and subtracting vectors using IJK notation, the tabular layout makes calculation easier. With the tabular approach, it is just as easy to add or subtract 3 or more vectors in 2D or 3D. So let me take a number of examples. Let's first of all take a straightforward addition of 2 vectors A plus B. Note that the components of A, B, and R may be positive or negative. So we fill our table. Normally we'll be given the magnitude and the angle from which we can calculate AX and AY. Similarly for B, calculate BX and BY. Then it's just a matter of adding the X components and adding the Y components to obtain RX and RY. Now normally we need to find not only Rx and Ry, but we also want to find the magnitude R and the angle phi that the vector R makes relative to the positive X axis counterclockwise. And these are found, as we have said, from the formulae R squared plus Ry squared square rooted. This is just Pythagoras' theorem. Or by finding the angle theta, keeping in mind that we have to interpret the angle that we find according to which quadrant the vector lies. And as we have said, to determine the quadrant, once you've determined Rx and Ry, you draw your axes, plot your Rx, plot your Ry, depending whether positive or negative. Once you've drawn the vector R from the components, you know which quadrant the vector lies in. Then you can calculate the theta. Either you can include the minus signs, or as I prefer, take the magnitudes so that theta is always positive, and then use the formulas that we've discussed to determine the angle phi. And phi, the formula for phi will be relative to theta, will be determined by which quadrant the vector lies in. Now, the next example is adding 3 vectors. As I've said, mathematically adding 3 vectors or 4 vectors is just as easy as 2. For adding 3 vectors, we simply resolve each vector into its components and then add them to get the X component of the resultant and the Y component of the resultant. And then again, as always, to determine the magnitude, we just use our normal formulas. The angle is given by this and interpreted according to the way that we have discussed on previously. Similarly, adding vectors in three dimensions is really just as easy as 2. We just have to add an extra column for the Z component. And then, again, we have to resolve each of the vectors, but this time into 3 components. This probably is the only slightly more difficult part, but not really that difficult. I mean, if you draw your box, as I mentioned before, and then look for the sides, you can determine a little bit more difficult than 2 dimensions, but not too much. But in terms of the table itself, it's just as easy. AX plus BX, AY plus BY, AZ plus BZ, and so on. So once you've got our components, again, Pythagoras' theorem, but this time for 3 dimensions. The angle theta, again, is a little bit more complicated than for 2 dimensions. Essentially, this time we find the theta relative to the XY plane, the inclination. But some questions you'll be maybe asked to find, other angles relative to the vector and the coordinate system. But I think the easiest thing to picture is the angle of inclination relative to the XY plane. And so this formula is found by looking at the right-angled triangle made by the vector r and its projection onto the xy plane. Then you see that this triangle here is a right-angled triangle. The right angle is here. Angle of inclination is theta, is here. We need to determine the adjacent. We know the hypotenuse is just the z component. And to determine the adjacent, then we notice that this is the diagonal of this rectangle, or equivalently, this right-angled triangle. So if I make a right angle there, this is ry. So this, simply by Pythagoras' theorem again, is r square root of rx squared plus ry squared. So once we know this, and we know this, then we have tan theta is 10 to the minus 1 of the opposite over the adjacent. Our last example is example 4, subtraction of vectors. Again, this is absolutely straightforward as long as you keep this following important proviso. As we have said, think of subtraction of a vector as the addition of the negative of the vector. And this is what's crucial. The first vector you write it as before, but the second vector there's a negative sign in front of the vector. So we draw brackets and we put a minus sign outside of the brackets. And inside the brackets we put the component bx and by. And then the reason we put the brackets there is because bx may be positive or negative. Positive or negative. Now if it's negative, you need to take account of this. So it would be minus, minus, or make a plus. As I've drawn here. If the component happens to be negative, minus, minus will make a plus. The reason for putting this into the brackets is not to confuse it with the subtraction of the component. So this is the sign of the component, and this indicates that you're going to subtract the component. So as not to confuse situations where you get two minus signs, I always recommend you draw brackets and put the component inside the bracket together with its sign, whether it's minus or plus, and then you can proceed accordingly. I mean, once you've determined Rx and Ry, the formulas for the magnitude and the angle are exactly the same. And I think that concludes the notes on vectors. And let me say bye-bye for now, and I'll see you the next tutorial.